There we go. All right, so it's been a long day of lecturing for me. So if my voice just switches off at some point and you hear that weird squeak and all those funny things happening, just bear with me. I'm just going to carry on as if nothing happened. So let's just go ahead from, we stopped at a nice place the last time, which was the beginning of set theory. And yes, we need to go over this stuff today. So the basic idea behind set theory comes first in defining what a set is, and it's just an unordered collection of objects, right? So it's written in this form that we have down here. And this is a nice one. It's A is equal to 1, 2, 3, but it can be anything, just any collection of objects. So I could have even written here A is equal to, I don't know, letter A. Thor can be another element. You could draw peach here, anything, you know. A set can just have anything in it. And now we just need to learn a few things about how to denote things within a set. Firstly, we see that it's always denoted by these curly brackets, and commas are used to separate different elements in the set. So for the example I gave above here, I could say Thor is an element of the set A, just to learn some notation, right? That means Thor belongs to the set A. It's just a way of saying that. Or I could draw this peach symbol and say is an element of set A. That's also true. Or I could try to draw, I don't know, banana or something like that, and say that is it an element of set A? No, it's not. So the way to say that would be, that is not an element of set A. So if I wanted to say something is not an element of set A, I just say it is an element and I scratch that symbol out. That means not an element. Okay. Somebody talking to me? No, okay. All right, so element of set A or not an element of set A. Again, these are in the notes somewhere. It's right here. So you guys can read that up if you forget. And another example which is important to look at is this example right here. A set A defined like this, where the elements in the set are 1, B, and then the last two elements are sets themselves. So a set can be an element of another set. See right here, this XYZ, that's a set itself, but it's an element of set A. So here we could say, for example, XYZ is an element of A, right? But what we cannot say X is an element of A, because X is not directly an element of A, element of the subset, which is in A, right? So this here is not true. X is not an element of A, but the set XYZ is an element of A. So just a subtle distinction here. And the symbol that we see here, which looks like a 0 scratched out, just denotes another set. To be specific, it's an empty set. So we open a bracket and close a bracket and don't put anything inside. That's an empty set. So the 0 symbol here represents an empty set. Okay. All right, so again, because it's online and I only have an hour, there's some stuff I will skip over, but I'll try and cover all the important things. So some sets could be infinite in size, like this one here, the set of all even numbers. It goes 0, 2, 4, 6, and so on up until infinity. So the dot, dot, dot here means the set continues forever. It doesn't stop. Okay, and there are different ways to denote sets like this. A very mathematically rigorous way, maybe a bit unnecessary, but correct, is this way right here. Right, we'll look at some more examples of this going forward, but this here is basically just putting a whole lot of mathematical jargon here to say that every element here is an even number. So if I were to read this, it will say A is equal to, then we open a set and say, in the set X is an element of natural numbers. The double dot means such that, the backwards E means there exists, then it says N, small n, which is an element of the natural numbers. Open a bracket and say X is equal to 2n. So let me try and say that again one time without explaining things in between. This says X is an element of natural numbers such that there exists an n which is an element of natural numbers where X is equal to 2n. That's just a very complicated way of saying what's said here at the bottom in a simple way. X, the elements of the set is X such that X is even. So this is usually a nicer way to say it, much more simple, but this is also correct. It's just a more rigorous way of saying the same thing. And both of these just represent the set up here. Okay, so just to get you guys used to looking at these in different ways. Okay, and now an example. So this is one of those examples where you kind of learn a few things by doing these examples. So I'll show you guys. We learn a few more tricks here. If I can just zoom in a little bit, maybe, to make some more space to write. Okay, so this is an example, kind of like the notation we saw above, where we have different sets here being described. And the question is asking us, let me just read it. It says, describe each of the following sets both in words and by listing out enough elements to see a pattern. Okay, so in words is not necessary. In words, and so we just need to list a few elements so we can see a pattern. That's all we need to do here. So number one, now again, guys, interrupt me if you need to, because this gets a bit messy. I'll try and start without being too ambiguous here. So let's ease into this one. So for number one, we need to list out elements of the set. So we need to show that this is equal to, I don't know what it will be, 1, 2, 3, blah, 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 whatever it is. This is the kind of thing we want at the end. We want to see numbers. Is somebody talking to me? Are we good? Let's just check what the commotion is about. Chat. What's happening in the chat?
I think someone's mic was just on.
Okay, probably. Thank you. We've been covering since last week isn't in out is, but is something wrong with my brain? I'm trying to understand what's happening here. I've been covering since last week isn't in out
I think he means in our module manual.
Oh, okay, thank you. What we've been covering last week, it is in the module manual. It will be there because I took it from there to make these slides. So it's all there. Ryan, does it carry a lot of marks in the exam? Sometimes, yeah, the set theory part especially. The stuff before this, maybe not so much, but I wouldn't say we can discard it. All the stuff here. Okay, all this other stuff we've been learning before about, what's the word I'm looking for? About statements, all that stuff usually comes out more prominently from learning unit 5. So we'll get to that later, but from here, set theory is the most important. Okay. So anyway, not to lose too much of time, let me go back to this example. So as I said, we want to list up. Yes, how can I help you?
Do you mind if we can do the first one in words, just for I'm curious. Just the first one only, and then the rest we can just do by listing out the elements.
Yeah, sure, I can do that. I can do that.
Right.
So I was going to explain in words by just talking through it, but yeah, I will do that. So let's get going with that. So here we usually start by looking at the rule that they give us to define the elements in the set, and that starts from here. So this side after the double dot is what we look at first. So this is telling us x plus 3 belongs to the set of natural numbers. So it's easiest to just start listing natural numbers from the first one up until the end. So we know natural numbers start from 1. It goes 1, 2, 3, 4, and so on. And every time we list a natural number, we equate it to this equation they give us here. So what I mean is x plus 3. So take that, equate it to the first natural number, which is 1. Then we just keep on doing that. Take the same thing, equate it to the second natural number, which is then equate it to the third natural number, and so on. Right? We don't have to do too many. I'm just doing a few here so we can get an idea. And then you just keep on doing this. That's the first step. Right? The second step is to solve for x in each of these equations. Okay, so I'm going to do that in one step so I don't take up too much of space. Let me make an arrow here and show the solution. If I solve for x in the first one, x plus 3 is equal to 1, we will get x is equal to 1 minus 3, which is just minus 2. From the second one, we will get x is equal to minus 1. Here we will get x is equal to 0, x is equal to 1, and so on. Right, so see how from the rule, solving for x gives us the elements of the set. So these here are the elements of the set. Right, so if we were to write this as an answer, it would be minus 2, I don't know why this keeps on happening, minus 2, minus 1, 0, 1, 2, dot, 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 right? We see the pattern, so we can list out as many as we want to. So what I have in this box here on the right are the solutions. Just comes from following the rule, using the rule to solve for x for every element of the natural numbers, and that's our answer. So describing this in words, I don't know exactly why they wanted to describe it in words, because in words it would just be something like, how do we say this? Just starting from minus 2 and adding 1 to each element. That's one way to describe it. I'll say that again. Starting from negative 2 and just adding 1 to each element. That's one option to describe it. There's so many possibilities. I mean, you could say, what's the word I'm looking for? The list of whole numbers shifted by 2 to the left. Could say something like that. Possibilities are endless here, so it's a bit ambiguous. But yeah, you wouldn't usually be asked to describe these in words. Just listing out a few is good enough. Okay, so
sir,
now, yes.
sorry. So in the exam or in the test, should I like how would we answer this? Would it be like exactly the first, like the way the question is, then equals and then add the elements, or is there a way to word it out? Like once we've figured out the answers in that box, how do we put it out? Do we put it out the same way that you did here?
Yeah, you could do it exactly the way I've done it, because as long as I can see some working on the side, like what I've done, then I know how you worked it out. So what I've done here is, it will be good enough for me.
Okay.
All right. Okay, yes, that's a very good question, because we have to always be careful to get our marks showing enough working. Okay. All right, so number 2, you guys may notice number 2 is very similar to number 1. The only difference here is that we have an additional restriction on the left-hand side of the double dot. And all that does is it filters our data even further. And if I can say data, it filters our first rule even further. So the first rule here is the same. X plus 3 is an element of natural numbers. So I will do the same process here that I've done above, right? And I'll end up with this list here again. That will be my first step, to just redo this part and end up with this list. But now the final answer is filtered again, because what this is telling me on the left is I will take only natural numbers from this list that I've worked out. Now natural numbers start from 1, so that means everything from this line upward we don't consider, because those are natural numbers. So we consider everything going downward. Right, so this answer will be from that list, just 1, 2, and going on. Right, so again, see, notice it's exactly the same as number 1, except here there's an additional filter to take only natural numbers. Okay, that is, and these are examples where we learn a lot of new things. It's good to practice these afterward. Once we're done, check if you can recap it. 3 and 4 get a little bit strange, but let's try and ease our way into them. Again, we always start on the right-hand side of the double dot, but here we see there are 2 restrictions. There's one here, and there's another one here. And these 2 restrictions are separated by this downward triangle, which we might recall represents an OR. It's an OR logical connective. So let's not worry about that just yet. Let's just use these 2 rules to find 2 sets, basically like what we did above, but now we'll do it twice because we have 2 rules here. So the first one says x is an element of natural numbers. So just equate x to all the natural numbers, as I did before. So x is equal to the first natural number, which is 1, then x is the second natural number, which is 2 and 3 and so on. And usually then I would solve for x, but there's nothing to solve for here. This is already telling us what x is. So as this is good enough, we can leave it like this. That comes from the first rule. The second rule says negative x is an element of natural numbers. So I'll write negative x and equate it to all the natural numbers. 1, 2, and so on. You guys get the picture. And here we can solve for x, right? We have to because it's not giving us x directly. It's giving us almost x. So if we were to solve for x in each case here, which I'll do on the right, here I will get x is equal to -1, x is equal to -2, x is equal to -3, and so on. And here we go. These are the values that we wanted. Okay, so those are our two sets. And now what the rule is telling us is that we need x such that it is separated by the or between these two sets. So in other words, whatever x I have must belong to either this set or this set. Right? We need to build our solution such that that's true for every element. So let me write it down here. So how do I write an answer which belongs to either this or that? Well, in other words, we can just put them together. If you do that, if you just list these together literally, right? It goes from the one on the right goes through all negative numbers. We can see that -1, -2, -3. So I'll list this like in order. I'll say dot, 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 -3, -2, -1. There's no 0 though. It doesn't go to 0. Now the list that I worked out on the left starts from 1. It goes from 1, 2, 3, 4, and so on. Okay, now the question is, why is this the solution? It's because if I look at this, then every element in this list that I made here, or in the set rather, belongs to either this or this. And that's what the rule wanted us to get. So if I look at the first one, for example, -3, that definitely belongs to one or the other. -2 definitely belongs to one or the other. So every element here belongs to one or the other. And that's what the rule is telling me to construct. Okay. Sorry, did somebody have their hand up for a question? Let me check the
No,
chat.
no, no.
Yep.
It's okay, sir. I was just actually confusing these rules. I was just about to ask, why is it now negative when the negative sign crosses the equals? But then I just remembered another rule on top of that.
Okay. All right. That's okay. If you need to stop me and think aloud as well, that's okay. No problem. Okay, so number 4, we can see number 4 is pretty much identical except for one detail. Number 4 is identical to number 3 except for one detail. What was an or here is now an and. Let me take out that circle because it's distracting, but it's now an and. So in other words, the solution that I come up with needs to belong to both of these sets that I worked out, right? And what belongs to both of these sets? In other words, can I list out elements which, if I look at the element, it belongs to both? So I have to find things common to both of these sets, right? Usually that wouldn't be a problem, but here when I look at these sets, I don't see anything in common, right? There's nothing in common here. One is all negatives, one is all positives. There's no 0 anywhere. So if you don't find anything common, if you don't find any elements, you just write an empty set. That's your solution. Open a bracket, close a bracket, or you could write it like this, empty set, the symbol for empty set, either one. Okay. So again, guys, there's a lot of new concepts here, so I'd recommend practice these 4 questions. I'm not going to give you guys an ice task today. What I've decided, I'm going to give everyone a free ice point because this is a difficult section. What I want you guys to do working on the honor system, go and practice all the examples in this learning unit. That's enough work to do. That's a lot of work to do. And that's how you learn the stuff. Me giving you extra examples without getting the basics right is not going to be helpful. So we'll do that a bit later, maybe. Okay.
Hello, sir.
Hello.
Is it okay to assume that an empty set is a subset of every set?
That's 100% correct. Yes.
Okay, thank you.
You're welcome. All right, so special sets, again, you guys can read this up. We've kind of covered this before. They're just symbols for different types of sets, like the natural numbers, integers, rational numbers, just symbols given, right? Now, relationships between sets, there's only two things we need to take away from this. I'm not going to waste too much of time here. One of them is that if I had a set, for example, 1, 2, 3, that is completely equivalent to me writing 1, 2, 3, 3, 3, 1, 1, 2. In set theory, these two are completely equivalent. That's because in set theory, repeats don't matter. As soon as you see a repeat, it's as if it's not there. So I see repeats, that one, that one, that one, that one, that one. It's as if they're not there. So just remember, repeats don't matter. One more point. If I had 1, 2, 3, that's the same as 3, 1, 2. Order does not matter. Repeats don't matter. Order doesn't matter. These are two important things. Okay, now we learn the symbol for subset, which we see here. It's that thing that looks like a sideways U. Oops. And there's another one here, which this one means proper subset. We'll get to that in a moment. But here, a subset is just taking a set and making a smaller version of it. So here we can clearly see A is a subset of B. In other words, A is constructed out of B. We've taken elements from B to make A. Therefore, A is a subset of B. But we cannot say that. We can't use this one here. We can't use this proper subset. And I'll show you an example where we can. Suppose I said C is equal to 1, 2, 3, 4. Then I can say C is a proper subset of B. So we only use this symbol here when something is also equal to the set, right? We can see C is the same as B. Equals to, I use that word loosely. In set theory, we say proper subset. Okay, and there's one example down here using names instead of symbols. Same idea. Which one is true here? We have a set A, which is Thor, Loki, Thanos, and Iron Man. So at the bottom, it's asking us which is true. Okay, the one on the top left I'm looking at. So Thor, Loki, Thanos, Iron Man is a subset of Thor, Loki, Thanos, Iron Man. That one's not true because it's the same set. But the one at the bottom is true because even though it is the same set, we're using the proper symbol here, proper subset, which means it could be equal. Okay, so again, this is something you might have to read up, not anywhere else, just reread what I said here in case it's not sticking in your brain immediately. And that's okay. It's a lot of information. Okay, so this is the example we need to do today. Rough a lengthy one, but let's get going with it. Okay, determine which of the following true, false, or meaningless. And we are given a few sets above, A, B, C, and D. All of them have various elements, and all the elements are numbers, so it's consistent, which is nice. So which of the following are true, false, or meaningless? Let's look at one. One says A is a subset of B. Is that true? Is A a subset of B? I don't think so. That can't be true because A is bigger than B, firstly. So A cannot be a subset of B. 2 says B is a subset of A. Is that true? Yes, because it's made up of elements from A. 2, 4, and 6 are the elements in B. And all those elements are in A as well. So B is definitely a subset. 3, is B an element of C? Is B an element of C? No, that's not true. B is a set, and the set B is not found in C, so that's not true. Okay. Now here, this is where we kind of learn something from 4 and 5. 4 is the empty set an element of A. No, it's not an element. Right? It's the empty set. Let's look at A. A has a lot of elements, and none of them are the empty set. But 5 is kind of what we discussed just now. Is the empty set a subset of A? Yes, that one is true, because by definition, the empty set is a subset of every set. It's almost like a philosophical kind of thing. The basis of every set is emptiness, and upon that, we build every other set. Okay, sounds almost spiritual when you say it like that, but that's the idea. 6 is A less than D. That is meaningless. You cannot compare sets like that. So I'm just going to say M for meaningless. Okay, 7 is 3 an element of C? I don't know, let's check. C has elements 1, 2, and 3, so yes, 3 is an element of C. So that's true. Is 3 a subset of C? No, that's not true. 3 is not a subset of C. Okay, this is where it gets a bit strange. 9 says, is the set 3 a subset of C? And to that we say yes. And this is where we kind of learn something new, which honestly makes me a bit uncomfortable, but it's the way set theory works. You can take any element of a set, an individual element, and consider it to be a subset if you write it as a set. But this only works for individual elements. So I could have also said 1 is an element of, sorry, not element, a subset. 1 is a subset of C. You could also say that. You could say it for any individual element. You can turn an element into a subset by writing it using the brackets. Yeah, I don't really like that, but apparently that you can do in set theory. Seems a bit like making up our own rules, but that is the thing we can do. Okay, a few things we have to learn here. One thing is called a power set. A power set is just, how do I say this concisely? A power set is a set containing every possible subset that can be made from an original set. So here, for example, do we have a place to write this example down? No, okay, so let me just do it up here. So the power set of A will be given by this right here. Power set of A is a set containing every possible subset we can make from A. So first, let's consider the individual sets we can make. We can make a set 1, 2, 3. Those are possible subsets. Then we can make the combinations with two things, 1, 2, 1, 3, 2, 3. Right? Order doesn't matter, so we can't now replace or add new things that will be, for example, 2, 1, 3, 1, 3, 2. Those are the same as what we've written, right? Because order doesn't matter in set theory. Okay, now with 3, we just have one combination we can make. 1, 2, 3. One more element we can write here is the empty set, because that is also a subset. And that's everything. Let me just check. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's right. So this is all the possible sets you can make from set A, all the possible subsets that you can make from set A. Okay, and now we learn the word cardinality, which is a fancy way of saying the size of a set. So if I ask you the cardinality of A, for example, we would denote this using something that looks like an absolute value. Cardinality is just 2 lines, and then you put the set symbol inside. And the cardinality of A is just the size of A, which is 3, because because A has 3 elements. And the cardinality of the power set of A will just be the number of elements in the, you can count and check now. It's 1, 2, 3, 4, 5, 6, 7, 8. It's just 8. So again, I just counted all the elements. Okay, that's cardinality. Right, what else is important here? This is pretty much things we've done already. You guys can try that at home. This is important stuff. You know, this comes out all the time, and we will be seeing this over and over again. The words union and intersection. So you have to learn what's the union and intersection of sets. So let's just learn by example here. If I have the set, they give us the set A is equal to 1, 2, 3, and B is equal to 2, 3, 4. The union of them is literally just, you take the word union, means unite. So you literally unite them together. So the A is symbol for union is just like a U, which is helpful to remember. A union B is just combining these two together. I'll say 1, 2, 3 from the first set. From the second set, we get 2, 3, 4. I just combine them together. And because repeats don't matter, we can rewrite this more concisely as 1, 2, 3, 4. Right, you don't have to show the intermediate step that I did, but I'm showing you guys there that we literally just take A and B and put them together and make one big set. So that's a union, very simple to remember. A intersect B, which has the symbol that's like an upside down U, that's A intersect B, is finding elements that are common between A and B. So in A and B, the only things that are common are, let's see, 2 and 3. So that's your answer there. It's a set containing the elements which are common between both. Okay, so this is union. This is, oh, that's very bad. Let's do that better. This is union. And this is intersection. It's very bad, but you guys can hear me speak and the words are written down here. So hopefully that's okay. Okay, lot to go over, not a lot of time. Universe and complement, two new things we have to learn. A universe is a bit of an abstract idea, but it's usually, you don't have to worry about it because it's always given to you in examples. A universe in the context of any example is just a large set from which all other sets in your example are taken or made, right? So a universe, for example, would be this right here. All the numbers from 1 to 10. Then if that's the universe in your example, every set that you look at must be a subset of the universe. So you can see here, the set we're looking at is A. That's one of the sets we look at in this example. It's definitely a subset of the universe, right? So the universe is kind of like all allowed numbers, all allowed elements rather. Okay, so we need to define, yes.
How's that different from a power set?
Because a power set is a set of all possible subsets, right? A universe is just all elements that are allowed. So it's a subtle difference. Universe is all allowed elements. A power set is all possible subsets. Yeah. Okay, so again, subtle difference, but yeah, you guys will get used to these subtle differences as we go. Don't worry too much about it if you don't remember them as I'm doing it. That's okay. All right, so yeah, a universe doesn't really deal with subsets, so maybe that's the key aspect here. Power set is looking only at subsets. A universe is looking only at elements. Okay. All right, so once we define a universe and we define a set, we can define a few sets from a universe, but here we're looking at only one, which is A. Once we have that, we can then define what's called a complement. A complement relies on the definition of the universe. A complement is every element in the universe excluding what's in our set. So for example, the complement of A, I'll write it like this, anybody, is basically everything in the universe. I'll start with that. Let me list everything in the universe. 5, 6, 7, 8, 9. But from that, we exclude everything that's in A. So whatever's in A, I'll just scratch out. 2, 3, I missed 5 somehow. Oh, it's here. 5, 7. Those are the things in A. So the complement is just 1, 4, 6, 8, 9, and 10. Is that what they have on the left here? Yes, it is. So that's an easy way to remember it. Everything in the universe exclude whatever is in our set A. That's a complement. Okay. So set difference is a very similar idea. Set difference is what we have here on the right-hand side, A slash B. We usually say this as A exclude B. So if I have a set A, let's just make up a set. A is equal to 1, 3, 5, 6, and B is equal to 5, 6. Then A exclude B is exactly what it sounds like. You take A, which is 1, 3, 5, 6, and just exclude whatever's in B. So B has a 5 and a 6, we just exclude that. And we end up with 1 and 3. Okay, yes, we have a question.
Sorry, I just missed the part with the small n. I know the upside down n would be the universe, and then the small n looking thing is what? Sorry, I missed it.
No problem. Is that this one here you're talking about?
Yes.
Okay. That is called an intersection, and it just means you find the elements that are common between both the sets. Yeah, that's what that is, intersection. Okay, but again, guys, if you forget these words, just remember it's all written up here. Yeah, and also the video will be available. All right, so it's okay. Don't stress if you missed it. No worries. Okay, so now we looked at set difference. Yeah, so I think the next thing we should do is look at this example. We need to get through at least this today. This is important stuff. Okay, so we have a few sets here defined as well as a universe. And you guys will notice the universe is always the biggest set, has to be that way. Given all of these sets and the universe, can we find the sets defined by 1 through 9? Looks like a lot of work. So let me test myself and see if I can do this in time, while also not confusing anybody. Sounds like a challenge, but let's see. So A union B is the first one. A union B, again, is just going to be A and B together in one set. So you can, I'll do the first one the long way. I'll just write the entire of A here, 5, 6, and then comma, write the entire of B, which is 2, 4, 6. And remember, in set theory, repeats don't matter, so I just don't write the repeats. So everything that's a repeat, I'll only write it once. So I'm writing 1, 2, 3, 4, 5, 6. Then what do we have? We have a 2, which is repeated, so I don't write it. 4 is repeated, so I don't write it. 6 is repeated, so I don't write it. So that's all we have without including repeats. And this is just the same as A. So I can write that if I want to. You don't have to, but you can write it like that. So A union B in this case is just A. A intersect B is whatever's common between A and B. And the common elements between these two is just 2, 4, and 6, if I look at it quickly. And that's just B, isn't it? So the common elements are just whatever's in B. Okay, 3 is B intersect C. So is there anything common between B and C? Yeah, I think 2 is the only thing common between B and C, unless my eyes are failing me. Yeah, it looks like it to me. 2. Okay, 4 is looking for A intersect D. So what's common between A and D? It doesn't look like anything's common between A and D. So the answer to that will just be, we can write the empty set like this or like this. Preference is up to you. Okay. So for 5, we might have to do a little bit of work before we can write the set. It will be and B union C, and then we can find the complement of that. So let's make some space here and first work out B union C. That, let's write it the proper way, just a U like that, B union C. Okay, so B union C is given by combining B and C together. So that will just be 1, 2, 3, 4, 6. Did I miss anything here? 1, 2, 3, 4, 6. I didn't repeat the 2 because we don't have to do that. Not necessary to repeat things. And now B union C complement is just everything in the universe excluding what's here. So I'm going to write it the way I did the last time because I think that's the least confusing. I'll first list everything in the universe. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And from here, exclude everything which is in B union C. So that's just 1, 2, 3, 4, and 6. Whatever is the answer, that's the complement. Or rather, whatever's left is the complement. So what's left is 5, 7, 8, 9, 10.
Sorry, can you
Yes.
can you just explain number 4 quickly for me? I think I'm getting confused because, like, with the whole definition of an empty set is a subset of any set. So
Okay.
that is sort of confusing me with number 4's answer.
A intersect C. Yeah, so I get you because the empty set is not an element of these sets. So it's weird to say that it's a common element. Yeah, so let's see if I can think of why they do this. Again, I'm taking this from the memo here. A intersect D. So somehow whenever nothing is common, we also just give the answer empty set, because empty set is somehow also equivalent to saying 0 in set theory, or saying nothing. So yes, I agree with you. It kind of is not exactly common with what we said above.
Yeah.
Yeah. But okay, that's a good point. Let me check that up and get back to you. I got you
Okay.
guys on WhatsApp, right? Yeah.
Yes. Okay.
Yeah, okay. So let me check. Yeah, sorry, I don't want to waste too much time, but that's a good question. When you bamboozle me, I appreciate it, making me think about things. Okay. All right, so where was I? Was on 5. So we answered 5 already. Let me just put the final answer here. 5, 7, 8, 9, 10. 6 is A exclude B, which is a similar thing to what we did in 5. Let me first list out A. Easiest way to do it is to first list A, which is just 1, 2, 3, 4, 5, 6. And from this, we just exclude whatever's in B. So B contains 2, 4, and 6. So exclude that. 2, 4, and 6. And then the answer is just what's left. I'll write this here on the left. Whatever's left is 1, 3, and 5. Okay. All right, now the big one, number 7. This is going to take a bit of doing. So let me make some space here. Again, this is all in the video, so it's okay. Make some space here. There's a quicker way to do this anyway. So we need to break this up into increments. First, let's work out this bracket on the left, maybe D intersect C complement. But to work out that, we first need C complement. So let's start there. We start as small as we can. C complement is just whatever's in the universe, but not in C. I'm going to do that in one go. I don't want to waste too much time. So what's in the universe, but not in C is 1, 2, 3 is out. 4, 5, 6, 7, 8, 9, 10. That's C complement. So now the next thing to work out would be D union, sorry, not union, D intersect C complement, which is just whatever's common between D and this new set we worked out. So where's D? Can't find it. Oh, it's up here. 7, 8, and 9. So what's common between that and what we worked out? In fact, it's all of those. 7, 8, and 9. Those are all common. Okay, so now we've worked out this part on the left. The part on the right involves A intersect B, all complemented. So let's first work out A intersect B. In fact, I think we've done that already. Question 2, yeah, we've done that already. So that was just 2, 4, and 6. Can we now take the complement of this? Yes, we can. Everything in the universe excluding what we just worked out. So that will be 1, exclude 2, we'll put a 3, exclude 4, 5, exclude 6, 7, 8, 9, 10. Okay, so now, what did we work out? We worked out this, which was the left-hand side of our number 7, and this is the right-hand side. Now we just need to take the union of these two sets. So the union of these two sets is going to be, that'll be the answer. So that's just basically the second set. Yeah, it's just 1, 3, 5, 7, 8, 9, 10. Combining that with the other set elements, which are 7, 8, and 9, those are all repeats, so we don't have to write them. So this is the thing. Okay, and 8 and 9, somewhere here will come up with a similar issue that that was just brought up about the empty set not being an element. But anyway, I'll check up on this because these answers that I'm taking, I've checked them up already. So they've, like, especially these easier ones, the simpler ones to remember, are from the solutions, from the module manual. So it's not incorrect. Yeah, anyway, I'll check these out. Let me not waste too much time. 8 says find the union of the empty set and C. So where's C? C is 1, 2, 3. The empty set is just the empty set. So the union of that is just going to be C. Right? You're combining nothing with C, you just get C. Okay, now what does the empty set and C have in common? That is going to be just the empty set. Okay. Now this number 4 is bothering me a little bit, but anyway, I don't want to waste your time figuring it out. I have a few more minutes. And this is important because it always comes out. This is easy because it's a memory game. Thing called a Cartesian product. I'm just going to do one example here for you guys. You can look at this one that we have here in your own time. I'll do a simple one. If I have two sets, A is equal to, I don't know, let's call it A and B is given by 1, 2, 3, for example, then the Cartesian product between these, right, as A cross B, is just a set made up of every possible coordinate that can be made from the elements in these sets. So it sounds weird, but it's a simple thing to write. It's just a set, and then in the set, we make a coordinate. The first thing right in the coordinate is the first element of A. Compare that to the first element in B. So A and 1, we just put them together. Then still with the first element of A, we do the second element in B, which is 2. First element of A, third element in B. So everything from B has been done with the first element of A. Then we say comma again. Now the second element in B, and then with the second element, everything from, sorry, the second element in A, right? That's what I'm doing now, which is a B. It's a small b. Okay, so that B with the first element in our set B, which is 1, then B with 2, then B with 3. Right, you see, it's just an ordering thing to kind of remember. Okay, and here's a nice bigger example done above here for set A, B, C and set 1, 2, 3. We see just as we've been doing here, first one from here, A, then with combining with each element from B. Then the second element in A, B, combining with each element in B. Then the third, combining with each element in B. So just need to remember the order. This is just a memory game. There's nothing more to it. Okay, I think we're almost done with the set theory part, which is good. Yeah. Okay, so now we look at Venn diagrams very quickly. Actually, guys, I'm going to leave that for you to read up in your own time because it's not too bad. We should probably try and hit sequences while we can. Okay, a sequence is just an ordered list of numbers. Similar to a set, but it's not really looking at elements. We're just looking at some kind of ordered list of numbers. Here, order matters. So that's the way it differs from the idea of set theory. So for example, here 0, 1, 2, 3, 4, 5 sequence. Okay, and examples of sequences are down here, just weird looking sequences, but these are sequences. Now let's make it more precise by defining them in terms of two things, closed formula and recursive definition. So again, it doesn't help me just reading these stories. Let's look at concrete examples of what these are. So closed formulas are this right here. Let's look at one, for example. This is just something where we need to substitute a value of n to get that element in the sequence, right? So we know, again, sequences are things like 1, 3, 7, 10, whatever, right? So how these formulas here, this one here, for example, tells me how to get any element in the sequence. If I want the first one, for example, I would say A and substitute n is equal to 1. Let me just check, does it start from 1? Sorry, I'm sure it does, but n starts from, it starts from 0 here, but at the bottom here it says natural numbers. So it should start from 1. Natural numbers start from 1, right? So forget about that 0. That's probably a typo. Too many typos in these notes, guys. It stresses me out a little bit. But here, okay, so it starts from 1. Oh, wait, but this is greater than or equal to 0. So it starts from, oh gosh. Two places now say it starts from 0. one place says it starts from 1. It probably comes from the fact that back in the day, a few years ago, they used to define natural numbers as starting from 0. Now they define them as starting from 1. Okay, so when there's ambiguity in the exam, I'm always going to just give you guys the marks. Don't stress about it. But let's go with the fact that they start from 0. Starts from 0. 2 places say so, so let's do that. Okay, starts from 0. So where was I? Yes, the formula, how to get a certain element of sequence. If I want the 0th element, I just substitute n is equal to 0. So we'll write this as a0 is equal to 0 squared. All I do is substitute into the formula, 0, right? So 0 squared is just 0. So this tells me the first element of this sequence is 0. Let's work out another 2. a1 is equal to 1 squared, which is 1. a2 is equal to 2 squared, which is 4. So this sequence, these are elements in the sequence, 0, 1, 4, and so on. So a closed formula like this is a very nice direct way to work out elements of the sequence. It's the ideal case. It's ideally what we always want to get, but it's not so easy to always get these formulas. Unless they give them to you, they are a bit of a mission. So usually we use this recursive definition, which is a little bit more natural, more common. So the notation is bad here, but yeah, let's look at one example. So this first one, we look at the first one here, and there's an example at the bottom which says find the first 3 terms for 1, 2, and 3. Let's just do 1 for now. Find the first 3 terms for what I just highlighted here. So let's look at the formula nicely. It will look like this. an is equal to 2an minus 1. These are subscripts here, with a naught is equal to 1. So a naught equals to 1 is just an initial condition. We're usually always given this. So list the first 3 terms for 1, 2, and 3. Again, we're doing this for 1. So we start from 0, right, as we just discovered above. So a0 here, I'm just substituting. Okay, let me write it clearly. I'm just substituting n is equal to 0 for the first one because we start from 0. So this will give me a0 is equal to a to the 0 minus 1, which is 2a to the minus 1. So that one doesn't help us so much because minus 1 is below our initial condition. We're given something at a0. So what I just wrote here doesn't help us much, but that's okay. We have to sometimes list them out to figure out what works, what doesn't. So let's go to n equals to 1 and see if that helps us. From the formula, this will now be a1 is equal to 2, a n minus 1 is just 1 minus 1, or a0. And that does help us because we're given a0. So I can write this as 2 times a0 from above, right here, is just 1. So 2 times 1 is just 2. So we got something. We have an element. So let's keep a list on the side. We know a0 is 1. We just worked out that a1 is 2. So that's another element. And once you got 1, you can see that you can keep it going quite easily. If I did the second one, just substituting to the formula, I get a2 is equal to 2a1. Now we know a1, we just worked it out. So this becomes 2, a1 is what? We worked out to be 2, so that's 4. So a2 is 4. Let me just do one more. N is equal to 3. We get a3 is equal to 2 times a2, which is 2 times what we just worked out, 4. So that's just 8. So a3 is 8. So this is why they call it a recursive definition, because based on what you worked out before, you can go ahead and work more things out in a recursive way. Okay, and here's an example. I'd like to skip that for time, but it's probably a nice one to do. Yeah, okay. Let's do this one. At least let me do a few elements here. This is a typical example you will get. Find a6 in the sequence defined by this recursive formula with 2 initial conditions. Find a6. So let's just start immediately from what they're asking us to work out, and then we'll keep on going backwards until we find a point where we know something. So I'll just write the formula firstly. an is equal to 2an minus 1 minus an minus 2, with initial conditions a naught is equal to 3, a1 is equal to 4. Okay, so the question says find a6. So what we can do is just start immediately there and work backwards to see what we need. So a6, according to the formula, is what we get for n is equal to 6. Right? If n is equal to 6, I write a6. I'm just repeating this formula at the bottom for n is equal to 6. That gives me 2a to the 6 minus 1, which is 5, minus a 6 minus 2, which is 4. Right? All I've done is sub n in. That's all I've done. Right? But I can't work out a6 because I don't know a5 and I don't know a4. So I'll keep working backwards until I find those things. So for a5, I plug n equals to 5 into the original formula, and I get a5 is equal to 2 times a. 5 minus 1 is 4, minus a 5 minus 2 is 3. I don't know a4 and a3, so I still can't do anything. So still, we have to keep on going. Let's try and work out a4, so I can back substitute everything once I get all of these values. So n is equal to 4. From the original formula, I then get a4 is equal to 2 times a. 4 minus 1 is 3, minus a 4 minus 2 is 2. Okay, we're getting closer, but not there yet. Still can't do anything. So let's now try and work out a3. Maybe that helps. N is equal to 3. a3 is equal to 2 times a2 minus a1. Okay, now we're getting somewhere because I know what a1 is, but I still don't know a2. So I still need to do one more step of this. Okay, so one more step, n is equal to 2. That gives me, according to the formula above, a2 is equal to 2 times a 2 minus 1, which is 1, minus a 2 minus 2, which is 0. So this last step, we can work out a2 because we know a1 and a0. Those are given in the initial conditions. Right, so I can work this part out here. 2 times a1, which is 4, minus a0, which is 3. Okay, and now this just becomes adding, subtracting, multiplying all of these things. So this is 8 minus 3, 8, 7, 6, 5. So a2 is 5 in this case. Right, and remember, guys, with these things, never trust yourselves. Always keep your calculators handy, especially in exams, because silly mistakes happen all the time with these things. So anyway, we worked out a2. a2 is equal to 5. And you can just keep back substituting here. We know a2, so now we can plug it into what we had here, because there we now know a2. Just do here. We know a2 and a1 we also know. Then from there, once you work it out, you will then know a3. So a3 becomes a known. Then you sub that in because we know a3 and we know a2 as well. Then we know a4, we sub a4 back in here, and so on. Keep on going back until you find a6. Okay, so that's the thing that you guys can try. Unfortunately, we have run out of time. And yeah, so anyway, even this example that I wanted to do today was the last important one. Although it never comes out, it's a nice one to help you think about these things. But the solutions to this are in the module manual, and there's a lot more detail there. So maybe have a look at that. Functions, is this the last section here? I think so. Functions, after functions, what? No, that's the last section. So the last thing you guys have to try to study by yourselves is functions. I'll try and make some questions regarding these. Oh, I don't want to make promises, but I'll try to. Okay. For questions, if you guys have. If not, it's okay. I know it's a lot of information.
Hi, sir.
Okay, maybe I should look at the chat. Oh, a lot
Yes,
of
sir.
stuff happening. Hello?
Will we ever have to find the formula ourselves, or will we always be given the formulas?
You will always be given. Yeah, that's the good thing about this section. Yeah, question and answer, they're very good. Okay, guys, I'm going to let you go now. I appreciate your attention. Have a good one, and I'll see you guys next week, Monday. I'm still here for questions, though. Jared, yes.
Sorry, sir. So for that last example, would it be like incorrect if we start from N0 or N1 and work our way down instead of going 6, 5, 4, 3?
No, that's perfectly fine. In fact, some people prefer to do that. So yes, you can do that.
Okay, perfect. Thank you, sir.
Hey, you're welcome. Don't worry, guys. I don't mind the shenanigans. I'll struggle as much as I can to give you as many marks as possible. And for most of you guys, it must be tough because you're working as well as studying. Yeah. Maybe I should stop the recording here.